don't. So let's start with what I'll be talking about over the next few minutes. So my clicker stopped working. So we as humans, we see the world, and we'll be talking about the visual cortex. We'll talk about how previous work has been doing what I'm doing currently. We'll talk about the improvements that we have made over the last 6 months of research. And we'll talk about exactly how we generate these MEIs via digital twins. We'll have a few different analysis steps of before we actually use the networks to after we actually use the networks. I'll show you more of these little blobs, and I'll talk about what they mean of what these MEIs actually are. And then we'll have some more analysis steps, don't worry. So we as humans, we rely on vision. And so we as neuroscientists investigate what a neuron represents in the visual cortex. Visual processing relies critically on the visual cortex. In humans, it starts in the back of the brain over here. In mice, it's also in the brain. Happens through different steps. Information flows hierarchically through different areas where information comes in first through the retina, hits the eyes, and then goes into the visual cortex in the back of the brain. And each visual area focuses on a different thing. Information flows from one area to another. And so these areas are organized in a hierarchical manner. That's what I just said. Great. So here's an example of the mouse visual cortex. So V1 is the primary visual cortex. This is where information comes in. We were interested in this other area just to the side of it, PM, or posterior medial cortex. And there's a bunch of other areas that do other things. If you need the acronyms, let me know. So yeah, the posterior medial, the PM is how I will be referring to PM and V1. And higher visual area does more complex calculations and representations than V1 does. So which subpopulations, which parts of these were we most interested in? So we were investigating 4 neuronal subpopulations across V1 and PM. And here's a little cartoon. So here's V1, here's PM. And we were investigating feed-forward and feedback connections specifically within these 2 areas. So feed-forward connections of neurons that go from V1 to PM, feedback connections that go from PM to V1. And so here's 2 subpopulations. And then we were also interested in their counterparts, right? So neurons that don't project to PM, neurons that don't project to V1. And we wanted to ask ourselves the question of what the neurons represent, what is represented by the neurons in the visual cortex. Is that more similar to the neurons to their neighbors or the targets of where they project? So how do we go around doing this? We acquired a data set of mice that are shown natural images. We put the mice on a little treadmill. I'll show you in a second. And we simultaneously recorded from both V1 and PM these 2 areas in order to investigate how these neurons respond. So here's a little mouse. Over here, you see the mouse. And the mouse is, of course, running on a little treadmill. And it goes run, run. So these are the images that the mouse sees. Important to know is that this is in 3 times normal speed. And we are recording. So we're recording from these 2 areas here, from V1 and PM. I'll zoom this in just a little bit. And so this is the live recording from the neurons in each area. So if we zoom in on V1 and PM, the green color, the green channel is GCAM. This is neuronal activity. The red color is neuronal activity of specifically the feed-forward and feedback projection neurons. So we injected TD tomato into V1 and PM. And so red is only the neuron. Red in each area is only the neurons that are coming in from the other area. So data set was formatted in a few different ways. We recorded the calcium traces. This is what the data set looks like. I will go through it a little bit step by step, but if you have more questions, please ask them at the end. So each visual bar is a trial. So we presented a trial being a natural image being presented to mice. These natural images are what you saw in the video last time. It's images of birds, cats, the sky, whatever, images of the natural world. And the mice have 3 different monitors that are in front of them. We rotate the natural images, so on. So each trial is a presentation of the natural images for half a second. Then we turn the screen off for another half a second. And you can see my arms aren't quite long enough to reach all the way up there, but you can see the calcium traces. So for example, for some neurons, everything above the video PCs, those are each individual neurons. For some of these neurons, there's an image that's presented that the neurons like, and the neurons fire. You can see each of the 4 subpopulations above, where we're interested in the labeled and unlabeled neurons, so the feed-forward and feedback projection neurons. We also recorded principal components from the videos to see how much the face is moving of the mouse. And we also recorded behavioral states of the mouse, so how big the mouse pupil is, change in the pupil size, the pupil position, as well as the mouse running speed. These are all variables that affect how neurons fire, how neurons function within the visual cortex. So we know that even within the visual cortex, the activity of neurons changes based on the behavioral state. Now, what do we do with this? We are interested in understanding the features of neurons that the neurons are tuned to. So what do individual neurons, when they look at the world, what do they get excited by? What do they understand? And previously, there were a few different ways of how to do this. So I will go very briefly, over 2 traditional techniques, sparse noise and the response triggered average, where we built upon this and we have solutions for some of these problems that come up with these techniques. So sparse noise is you present dots and gratings to the mice. And you say, okay, in these areas, which neurons fire? So here's an example image presentation of sparse noise to the mouse. And then you can predict how a neuron responds in what areas of the visual cortex. So here's an example neuron. And so you can say that for this neuron, it likes either black or white dots in that area. Cool. You can also, however, the problems with this is that you're not getting features, right? You're saying, okay, black or white, just something in this area the neuron responds to, we don't know exactly what. One of the ways that historically people have solved this is by using response triggered average calculations. But the problem with that is that those are linear. So here, this is what we did for some parts of our experiments, where you present many, many, many images. We presented a few thousand to the mice. So here's some examples of the natural images that the mice saw. And then you can calculate on average which parts of the image a neuron responds to. So the response triggered average is that for all of the spikes where a neuron fires, average the images, and we can get information on not only where, but what a neuron is responding to. For example, let's say that for this neuron, we can see that it likes dark and light. Wow, incredible progress. But this has an assumption, which is that it's a linear assumption. And we're making an assumption of linearity here. So how do we solve this? We used our data sets to train a digital twin model to essentially take the visual cortex of the mouse, put it inside a computer, and then we can ask it more questions. So essentially, the in silico model predicts neuronal responses to images. We train it to predict the responses of neurons to the images that it sees, that the mice see. This allows us to ask more questions such as for us, what do the neurons respond to? What do the neurons appreciate that would be really, really difficult to ask in a biological setting? And I'll get to this in a little bit. And then we can generate these little blobs that you saw at the beginning, the most exciting images for each neuron, by conducting gradient ascent in the image space. So if you have a neuron of interest, we say, okay, how do we need to change the input image in order to make it fire more? I'll talk about the experimental setup a little bit. And like I mentioned before, these MEIs, they help us better understand neuronal representations. And allow us to have nonlinear calculations of these representations. And we have two steps. We have a forward step where the digital twin, like I said, predicts the responses to the images that are coming, or the inputs. And then we can solve the reverse question. We can say, okay, I want to generate MEIs for the most predictable neurons. If we want this neuron to fire as much as possible, what do we need to give to the input as inputs? I'll very briefly go over how the networks are set up. They're set up like this, obviously. So we have incoming stimuli, which are both the natural images and the behavioral state of the mouse. The core network computes latent features from the inputs. And yeah, so here we have 1, 2, 3, 4 different modules. The core module computes latent features from the inputs. The readout network is learned per neuron, and it maps the core feature space to the responses. It learns where in the latent feature space each individual neuron lives. We also have a shifter network, which accounts for the eye movement. So if we're trying to understand how a neuron responds to an image, if the mouse moves its eyes, then different neurons are looking at that same part of the image, and that has to be accounted for. And then we have a final part of this, which is the modulator network accounts for the actions and the behavioral state, accounts for the actions of the mouse. We started off by training 5 models in an ensemble, and there's some assumptions that we can make, which in theory would help ensemble models function better than each individual model at once. We did not observe this. I'll go on into a little bit more detail later. And we also separately trained by area. So we trained a network both for V1 and a network for PM and saw the differences. So finally, let's talk about some results, the cool part. So even before we get to the results of the MEIs of the digital twins, I want to talk about how much each image stimulates each neuron. So of course, each image that a neuron sees do not stimulate all neurons. The V1 has a very sparse representation, or neurons in V1 have a very sparse representation of the visual cortex, visual field. And this is consistent with previous results, which is good. That means we're actually doing stuff correctly. Here's a graph. So each light blue line is the response of a neuron to all images. Most of the images elicit very low probability of activity in neurons. The y-axis is the probability that a given image will stimulate more than this x-axis of neuron. So you can see, and the red line is the mean of all of this. So you can see that for some neurons, it is likely that only very few images stimulate them. However, we have some outliers that are more stimulated by other images. Then in order to validate the results of the MEIs, once we predict them, we wanted to make sure that, first of all, they're in the right place, that they're able to stimulate the neurons that are, at least for this receptive field. So likely, they're accurate. Why likely? I'll talk about this in a second from our predictions. So we observed high correlations with predicted receptive fields locations using the techniques that I talked about before. So kind of the sparse noise technique is the one that we used here. And why I say correlation and not exact one-to-one is explained in this graph here. So the x-axis is the predictions of the locations of the receptive fields by the sparse noise model. The y-axis is the predictions of the MEI model. So if the receptive fields are being predicted in the same locations, we should expect a unity line. However, I apologize. However, we have different unit systems, which is why we do not observe a unity line, right? So you can see that it's not 1 and 1 on the y and x axes at the same time. The model is scaled from -1 to 1, while the sparse noise is the actual angles in the visual field. However, we still observe a high correlation between the location, right? So we can, R value of 0.9. This is for the azimuth, so the left versus right in the visual field. We can have the same for the elevation, and the accuracy of the prediction goes down a little bit, goes to 0.7. And this is both for V1, right? So this is for the V1 area. However, we can also calculate the same values for PM. We can say, okay, here's the predictions for PM on the bottom. And so for the azimuth, so for the left versus right, we actually have good predictions. For the up versus down, we start having issues with predicted correlations. And so we did this not just for one model. Like I said, we trained 5. But we ended up taking, instead of the ensemble model, we just ended up taking the best model for the task, best model for the job. So this is from this day from model 4. Now, I've talked a lot about MEIs, but what do they look like? Well, I showed you one at the beginning. Here's 80 more. Have fun. So I'll just talk about these a little bit before I go on to what to some analyses. These are, as predicted by our model, the most exciting inputs for each neuron, right? So for example, for this neuron here, I can use a laser pointer. For this neuron here, it likes the white in the middle and then kind of black around. You can see some kind of classical Gabor functions such as this, the way I had expected in V1 that there would be more of these. So this is the V1 and this is PM. So let's talk about them. So here's a different slide. Let's quantify them. Other than looking at them and being like, okay, wow, they're actually different. How are they different? So we can say that the MEIs in PM are significantly larger statistically than those in V1, which is as expected, right? Where in a downstream area or in a higher visual area has more complex representations of the world than neurons. As predicted. Again, we're on track. However, we see that some MEIs are noise, such as there's one there. And this may be because neurons are described by the behavioral state, right? The activity of the neurons is more described by the behavioral state of whether the mouse is running or not, as opposed to what the mouse is looking at. So this is cool and all, but how are these actually different, and what are the differences between the MEIs? So we did some dimensionality reduction. This is UMAP. And we plotted in on a grid, right? So we have a grid here, and each location of the MEIs on the grid in UMAP space corresponds to that MEI. So we observe that in UMAP space, the MEIs are very classifiable. There's kind of 2 clusters. There's the PM MEIs, which are crosses. Correct, yeah, they're crosses. There's the V1 MEIs, which are circles. This, unfortunately, is not as predicted and how other people have done it before, where in previous literature, those were a lot more mixed. So that's a great question to ask as to why that is the case. And the answer is that's for the PhD. So like I said, these MEIs are easily separable via dimensionality reduction, right? You can basically just draw a line here and say, okay, these are the PM MEIs, these are the V1 MEIs. However, the differences in the actual features of the MEIs is not so easy to see by eye. Right? So I mentioned that the sizes of the MEIs are different. That's not what the UMAP is looking at here, because we scaled the sizes. But I don't know, it's difficult for me to say that this one is significantly different from that one, and that I would be able to classify this in this manner. So once again, what's the difference? Read my paper, or to read the actual work. Now, this is cool and all, but we wanted to do one more investigation step. And we wanted to ask the question of how does the representations of neurons, of what neurons respond to, how is that influenced by learning? So whether that's innate genetically, or whether through development, the neurons learn, the neurons change their representations. So we had a bunch of mice that were raised in the dark, also known as dark period, where these mice have never seen anything before until we show them these images. And the question then becomes is, what is the most stimulating image? What is the most exciting image to a neuron that has never seen anything before? And the answer is, it's that. It's this. So we only have PM MEIs. So these are for the dark red mice. Those are for the normal mice. These are both from PM. Due to some issues with the recording, we only had time to get the MEIs from the PM area. And an interesting part of this is that the MEIs in this PM for dark red mice are significantly smaller than for normal mice, which is also not exactly what people have predicted before. So, and we also see a bunch of more MEIs that are kind of noise, right? So we kind of, there are fewer neurons in mice that have never seen anything before. There are fewer neurons that actually respond to the visual world and can more be explained by behavioral state and so on. So let's wrap up. We created a digital twin. We took a mouse brain, put it inside a computer, and then we asked it more questions than we could have asked in a biological mouse, right? There's no really good way to do gradient descent in the image space for biological mice, right? There's, images have a bunch of neurons and then a bunch of pixels, and you change one slightly, and then you record and then change another one slightly, and it takes absolutely forever. So we just did that in silico. We investigated 2 visual areas, V1 and PM, and we investigated the subpopulations of the neurons. And we also created MEIs for each area. We observed significant differences across the areas, but not really significant differences within each area. So we found that the feed forward and feedback neurons were more like their neighbors in each area than their projection targets. And we also saw that dark rays mice have smaller MEIs. Neurons are less responsive to light in general. Overall, with MEIs, we're able to capture nonlinear aspects of neuronal preferences, right? So for some of the MEIs, we saw circles, right, which is nonlinear. And overall, I think this allows us to have improvements over traditional techniques, allows us to ask more questions. Speaking of questions, are there any? Thank you. Yes. Yes. So we used AI during the generation of the code, right? We have coding helpers such as Copilot. That's the word that I'm looking for here. And of course, the entire thing is AI. Oh, someone said, would you mind repeating for us the question online? Yes, sorry about that. The question is, how did AI help with solving this problem? And of course, the entire thing is AI, right? It's a prediction of inputs. It's a classical neural network. It's basically what ChatGPT is doing in the current years. Other questions? If you have questions online, either speak up or just type them in the chat and I'll see them anyway. Yes. Uh-oh. Uh-huh. Hi. The inputs were, where did I put it? Yeah, here. So the question is about the dimensionality of the inputs. We have a few different inputs. So we have responses of neurons by trials. So we have a response matrix, which is trials by neurons for each area. We also have whether or not each area is labeled. We also have the behavioral state for each neuron for each trial, which is 5 by neurons. And there might be one more that I'm forgetting. Oh, and the actual natural image itself, of course. The output was essentially these calcium traces, right? So we're predicting the responses of the neuron, right? So yeah, sorry. Let me take a step back and make this a little bit clearer. So the inputs are the natural images and the behavioral state in some cases. And then the outputs of the neural network are the actual calcium traces. We have a data set that we can then, is labeled, and then we can do supervised learning. Uh-huh. So I have a slide that's very messy, but answers your question. So I'm going to show it. Um, mm, this. So for example, here, like I said, it's very messy. So we have the locations from each of the 5 models. I only showed the best one here, right? Because this is the one that we ended up choosing. But so this is each submodel that was for the ensemble for a specific training run, right? So for some of them, there's really poor correlation, right? And each model is not being able to identify what it needs to learn, what it needs to find, and so on. On average, because we're still taking an ensemble, it still works reasonably well. But if we're trying to generate the MEIs for them, I don't have an image for this, but we observed kind of one main MEI and then a bunch of shifts in image space, even if it's the same predicted MEI or predicted neuronal response, they were just literally shifted, translated in image space. And that was because each model was predicting a different location. And so in order to solve that problem, we just took the best model out of the ensemble. Yes. Thank you. Okay, so pretty good. Where is my, oh no. Okay, no one on Zoom can see my screen anymore. Hold on. I I don't have a slide that answers your question, but I need to share my screen again on Zoom. Um, we calculated the correlation between so not directly the accuracy, right? Because it's, changes over time. We calculated the correlation between neuronal responses and the predicted, Y and Y hat. And for some neurons, this was a different value per neuron. For some neurons, we got pretty high, so it's from 0 to 1, which is of about 0.8. But those were the outliers. For some neurons, it was, on average, for the best models, it was about 0.4, 0.45, which is also pretty good. I mean, and then you can draw the Gaussian, right? And it starts from 0, which is neurons that are, yeah. Jota, and then, right. Yeah, so the first question is, how did we choose V1 and PM? V1 being the primary visual cortex, PM being a downstream area. The answer is there was already a data set when I started working on this project that was being used to investigate other questions. For feed forward and feedback projection neurons, the question was whether or not those neuronal representations would be more similar to the area or the area that they project to. And can you repeat the second question? I am trying to find the MEIs. Yeah, so these MEIs, I mean, so you can see that between neurons, the MEIs are not the same, right? So the MEIs for this neuron here, for example, this is not the same as this one, right? And they're in different locations. So in theory, the theory goes is if you predict the MEI to a neuron, and then you show it back to the same neuron, it will be selectively most stimulating to that neuron. And other neurons won't be as excited about this. Practically, we did this experiment and we didn't exactly see this due to a range of other factors, but that's the theory, right? Right. Do you want to read them out for the class? That's true. So let's kind of go in order for the chat. There was a question of, do I have a hypothesis about the UMAP differentiation between V1 and PM? That is a question also for further research, where it is unclear to us at this moment what UMAP is picking up on, right? So UMAP being this thing, this dimensionality reduction technique. Just leave it here. Yeah, it's a little bit unclear to us at this moment what features of the MEIs of the receptive fields UMAP is picking up on, and these differences, where there might be some aspect that we are not controlling for. And yeah, so that's further research. Thanks, Ryan. And for the smaller responses in dark-haired mice, and so we know that the activity of the visual cortex changes with dark-haired mice. The question was, what are the implications of smaller responses for dark-haired mice, or smaller MEIs for dark-haired mice, where we know that the activity of the visual cortex changes when mice are dark-reared, even if you show them to eventually show images to them or show light to them, it comes back, but doesn't really quite get back to the same level of activity. And the answer of why we have smaller responses is, I think, still an open question and can be answered later, eventually. Hector, I see you have your hand raised. I think you should just be able to speak and everyone should be able to hear your voice.
Can you hear me?
Yes.
Okay, well, thank you, Anna, for this fantastic presentation. I wanted to ask you what you think are the advantages, but also the limitations of the specific method you're using. So using this artificial, how do you call it, identical twin or?
Twin, yeah.
Yeah, to investigate something about an organic being that is like the brain, right? Like, yeah, in general, what are the advantages and disadvantages that you have, I guess, learned during this project?
So the advantages are that it's in a computer, right? That you can ask it the questions, similar sort of questions as to what we did. You can train it much faster. Iteration is much faster, and you get all the benefits of it being a neural network. You can take apart the layers and you can ask questions through the layers, for example. One of the disadvantages is that this is, like everything else, just a model, right? And so you can have your networks predict whatever you want, but if you can't validate these results in vivo in the actual mice, then it doesn't really work. There's a question which was, how do you record calcium traces in neurons, which is using 2-photon microscopy. Essentially, hold on, we have where is this? Right here. You can look at the mouse running if you want. So we have 2-photon microscopy, a mesoscope set up where so this is GCamp. People who have taken classes with me before know what GCamp is, but essentially it's, I forget what it actually stands for, green calcium something protein something, where when there's calcium that's present, such as during firing, you can shine a light and you can shine specifically a green light of some green wavelength, which the number I also don't know off the top of my head. And then the neurons, then you can observe the firing of the neurons, because when there is more calcium, these proteins will fluoresce. Same with red. Where can we find your thesis to read it? It will be online somewhere, or I'll send it to you directly. How applicable are these results to the human brain is another question from online, which is, I mean, neurons also exist in the human brain, right? As far as I know. So you can make these calculations, you can present these MEI, you can, you know, do this to the human brain, but silly things about humans is normally you can't just drill holes in the skull and then put electrodes in. People usually don't let you. And so, but essentially, if we find other ways to do it, then this is non-invasive selective stimulation of neurons in the visual cortex, which is also quite a good purpose. Any other questions? Yes, you were first. Yeah, so the differences were quite literally just the different starting seed, which was a little bit surprising to us that for just different initializations, random initializations of the network, of the parameters of the network, they would either converge or not. Great question as to why. That's why we train 5 and take the best one. Yes. So we measured, fine, I'll put the slide on screen. No more mouse for you. So we measured the correlation, yeah, to the sparseness, but that was specifically for the receptive field location, as opposed to the location of the MEIs. But in order to train the model, we were training it, the data set had calcium traces. Yeah. What do you mean by calcium prediction error? Oh, yeah, it had a correlation with this. If yeah, the activity of the neurons, responses of the neurons would be poorly predicted if the receptive fields were poorly predicted. Other questions? Where would I like to see this research going in the future, and what other questions do I have that I've learned from it? I think I personally am a big fan of digital twins, which is partly why I did this, right? Like I said, taking a real brain and putting it into a computer is kind of cool. We don't need to talk about the ethical implications, right? That's not why we're here. We're scientists. Yes, I've taken an ethics course. Don't worry. Um, but I think that's cool, right? Especially as neural networks become more and more biologically inspired, right? So for example, ChatGPT, these transformer models, they're not biological at this point. For example, they take magnitudes and orders more of energy, right? And so if we can understand how the brain works and better, we can make better models, make better networks, so on. What was your second question? Yeah, so there's still a few open questions from this, such as why our models are different, why dark-haired mice have different MEIs, and the other things that I brought up. And so, yeah, it's for future people, for people who take up this project next. Matthias. Other questions? All right, anyone from online before we all go home? All right, well, in that case, thank you everyone very much for coming. And there will be a small little reception outside as soon as we set it up, so don't leave or I will be sad. And yeah, thanks.